Alright, let's get started. The paper I'd like to talk about today is called Neuroordinary Differential Equations. It was published at NeurIPS 2018 and won the Best Paper Award. And as of now, it has been cited more than 7,300 times, which shows just how influential it has been. So here's what we will cover today. First, I will give a quick introduction to the main idea behind neural differential equations. Then I will go over some basic math concepts about differential equations and numerical solvers, just enough to help us understand how these models work. After that, we will define the three main frameworks: NeurODs, NeurCDs, and NeurSCs. Next, I will explain why we care about neural differential equations and what makes them interesting. And finally, we will wrap up by looking at their theoretical guarantees, applications, and training methods. So let's talk about the main concept of neuroordinary differential equations. In traditional deep learning, we stack a fixed number of layers to transform inputs into outputs. But NeurODs work differently. They treat this transformation as a continuous process. Instead of defining discrete layers, they use a neural network to model how the hidden state changes and then solve an ODE with a black box solver to get the output. Before dive into neural differential equations, let's quickly talk about some mathematical background. So what exactly is a differential equation? Simply, it's an equation that relates a function to its derivatives. In other words, it describes how something changes over time. Differential equations are fundamental for modeling systems in many fields. Let's look at an example. The SIR model, which describes how an infectious disease spreads. By solving a SIR model, we can predict how the number of susceptible, infected, and recovered individuals change over time. Another simple example is the predator-prey model, which describes the dynamics of two species interacting within a biological system. However, unlike the previous examples, most differential equations can't be solved analytically. So we use numerical solvers to approximate their solutions. There are many solvers to choose from depending on the accuracy we need, and the simplest one is Euler's method. In Euler's method, we start from an initial point and estimate the next value by taking a small step along the slope given by the derivative. By repeating this process, we approximate the entire solution curve. Of course, you can also choose more advanced methods to obtain better and more accurate solutions. So, what are neural ordinary differential equations? In NeurODs, we represent the vector field using a neural network. To get our model's output, we start from the initial value y0 and solve this differential equation by integrating the neural vector fields over time until the final time step. If we go one step further, we can think about integrating not just over time, but over the data itself. In a standard ODE, once we set the initial value, the entire solution curve is fully determined. But when we have ordered input data, we can continuously incorporate incoming information into the dynamics. This gives us the controlled differential equation. Instead of integrating over time alone, we integrate over the input data. Here y is the hidden state of the system, and it is updated continuously as new observations X arrive. Intuitively, you can think of this as being very similar to an RNN, where the hidden state adapts to incoming data. Unlike a regular ODE, where the entire trajectory depends only on the initial value, a CD adapts dynamically as the data evolves. And finally, just like neural ODEs, we parameterize the vector fields with a neural network, and that gives us neural CDs. Finally, we take one more step. This time, the driving force is not the observations, but random noise. In the equation with the first term is usual drift, and the second term integrates over Brownian motion. if there's no noise, so when we ignore the second term, then we recover the regular ODE. But when we add the random diffusion term, we get a stochastic differential equation. You can think of this as a generalized framework. There is some hierarchy from ODE to CD to SDE. In experiment, you will see that SDEs can approximate both the deterministic and random dynamics, but ODEs cannot capture random behaviors. And finally, just like neural ODEs and neural CDs, we parameterize the vector field with a neural network, and that gives us neural SDEs. Now we have defined neural ODEs, CDs, and SDEs, and we have built some intuition behind these equations. But the real question is, why should we care about neural differential equations? What makes them interesting? Indeed, many of the most effective and popular deep learning architectures resemble differential equations. Let's recall the formulation of residual network, where f theta represents the residual block. Now think about the neural ODE formulation. If we discretize neural ODE using the Euler's method, we can recover the residual block formulation exactly. This observation shows that neural ODEs are the continuous time limit of residual networks. And once we see this connection, it naturally prompts us to explore other links between differential equations and modern neural network architectures. It turns out that neural-controlled differential equations are the continuous time limit of recurrent neural networks. In other words, just as neural ODEs generalize ResNet to continuous depth, neural CDs generalize RNNs to continuous time, continuously updating the hidden state as new data arrives. Even architectures like GRUs and LSTMs can be seen as applying update rules that resemble discretized differential equations. The connection to RNNs is intuitive. Just like controlled differential equations, RNNs compute a function of their time-varying inputs to update the hidden state at each step. As with other cases, a numerically discretized neural stochastic differential equations also has a natural correspondence in the deep learning literature. Similar to neural CDs, the closest analogy is an RNN, but here the input is random noise and the output is a generated sample. Now we know that with neural differential equations we can build continuous depth of deep learning architectures. But you might wonder, do solutions to these equations actually exist? And from a practical standpoint, what kinds of functions can these models approximate? Without loss of generality, neural networks are usually built as compositions of Lipschitz functions. Because of this, for most architectures, the existence of uniqueness of solutions are guaranteed. Under mild smoothness assumptions, neural ODEs are well defined, and Picard's theorem provides a theoretical guarantee that a unique solution exists. Similar results also hold for neural CDs and neural SDs, so these models are mathematically well-founded. You can find the formal theorems and proofs in the references listed below. What kinds of functions can neural ODEs approximate? Generally speaking, under mild conditions, augmented neural ODEs can approximate any continuous mapping. Interestingly, the vector field F itself does not need to be a universal approximator. The expressiveness comes from the continuous time dynamics. Similar approximation results also hold for neural CDs and neural SDs. You can find formal theorems and proofs in the references listed below. Now we know that we can actually solve neural differential equations and that they can in principle model any continuous mapping. Of course, these theoretical guarantees don't automatically ensure good empirical performance, but they do give us confidence that such modeling is possible in principle. So let's move on to the practical side. What kinds of problems can neural differential equations actually tackle? First, neural differential equations can be used for generative modeling. A notable example is continuous normalizing flows. As you know, generative modeling aims to run the target data distribution when we only have samples from it. The common approach is to start from a simple base distribution and run a mapping that transforms it into the target distribution. It turns out that some of the most effective mappings naturally arise from differential equations. For example, continuous normalizing flows transform a normal distribution into the target distribution. Normalizing flows transform a simple distribution into the complex one using the change of variables formula. However, standard flows require computing the determinant of the Jacobian, which is cubic in cost and limits model expressiveness. Continuous normalizing flows solve this problem by replacing discrete layers with a continuous transformation. In CNFs, the change in log density is given by the instantaneous change of variable formula, which only needs a trace instead of full determinant. This makes CNFs much more efficient, enabling expressive flow models with many hidden units at a cost linear in the number of units. Similarly, in score-based diffusion models, the mapping is defined by the neural SDE, where the dynamics are driven by Brownian motion. The second application is generative modeling as well, but this time we focus on time-varying data rather than static distributions. Here we aim to model distributions over time series. A key example is the latent ODE. It represents each time series as a latent trajectory determined by an initial state and latent dynamics. The model is trained as the variation autoencoder. The encoder processes the observed sequence and produces the approximate posterior for the initial state. Then, given this initial state and the observation times, the ODE solver computes the latent states at each time point and can even predict values at arbitrary time on a continuous timeline. The next example is SDE GANs. Previously, we saw that latent ODEs are trained using the variation autoencoder framework. This time, we train a neural SDE as a generative adversarial network. Neural SDEs are continuous time generative models for time series, and they can be fitted using Wasserstein GANs. Here's how it works. The generator is a neural SDE that takes Brownian motion as input and produces time-evolving sample path using a numerical solver. The discriminator is a neural CDE, which evaluates these generated paths against real data. By coupling the neural SDE and neural CDE as a generator-discriminator pair, we can train continuous time GANs that model distributions over entire path space. The third application is physical modeling, but this is actually a broad term that covers many different fields. In classical mathematical modeling, the mechanistic theory-driven differential equations are already widely used. However, at some point, these theoretical models fail to fully capture the complexities of reality. By combining existing theory with deep learning, using neural networks as high-capacity functional approximators, we can close the gap between theory and observation. For example, recall the Luca-Volterra model, which describes the interactions between the predator species and prey species. Here, x and y represent the population size of each species over time. This model is theoretically constructed, but in practice, its predictions often deviate from real-world observations. To fix this, we can augment the existing model with a neural network correction term. Let f theta and g theta be neural networks that run the residual dynamics not captured by the theory. This allows us to combine domain knowledge with data-driven learning for better modeling accuracy. There are many applications of this approach, including turbulence modeling, climate modeling for the ocean, Hamiltonian neural networks, Lagrangian neural networks. This synergy between differential equations and neural networks gives us the best of both worlds, interpretability from theory and flexibility from deep learning. The final application is challenging time series problems. In the real world, time series data is often messy and irregular. Different channels may be recorded at different frequencies, missing data is common, and sequences can have variable lengths. Neural differential equations provide a powerful framework here. By treating discrete observations in a continuous time regime, we can naturally handle irregularly sampled data and process it on the same footing as regularly sampled data. This makes them especially useful for fields like healthcare and anywhere messy time series data is common. Now we know that neural differential equations can model continuous dynamics, from generative modeling to time series forecasting and beyond. But here comes the key question: how do we actually train these models? There are two options for backpropagation through neural differential equations. The first option is simply backpropagate directly through the internal operations of the solver. A differential equation solver internally performs basic operations which are differentiable. The advantages are accuracy and speed, because we directly use the same computations from forward propagation, and the full computation graph is known, we can rely on automatic differentiation. However, it is memory inefficient because we must store every intermediate operation of the solver, which is sometimes infeasible for deep simulations. The second option is called the adjoint method. Instead of storing everything from the forward path, this method works by setting up a new differential equation that runs backwards in time. We then solve the adjoint equation numerically by compute the gradients. The advantage is memory efficiency, since we don't need to store the entire forward computation. But there are trade-offs. First, it is more computationally expensive because we have to recalculate y during the backward path. Second, we introduce truncation errors since the forward and backward solutions for y may not perfectly match. And finally, the adjoint equation itself must be solved numerically, which brings in additional numerical error. Let's take a closer look at what the adjoint method actually does. When we train the neural ODE, we need the gradients of loss with respect to model parameters. Now, instead of storing every intermediate state during the forward path, the adjoint sensitivity method computes these gradients by solving an augmented ODE backwards in time. Here's the idea. We define an adjoint variable. This measures how the loss changes with respect to the hidden state. The adjoint itself follows its own ODE, which is integrated backward from the final time all the way back to the initial time. While integrating backwards, we recompute the trajectory y and calculate two things at the same time: the gradient with respect to hidden state and the gradient with respect to parameters theta. All of these can be handled in a single call to the ODE solver. Okay, let's wrap up. Neural differential equations parameterize the vector field of the differential equation with neural networks, elegantly combine two dominant paradigms, neural networks and differential equations. Since their introduction, neural ODEs have inspired many extensions, such as neural CDs and neural SDs, and enables a wide range of applications: continuous time dynamics modeling, smooth density estimation, generative modeling, and handling irregular time series through continuous representations. Neural differential equations remain a powerful and evolving framework, with vast potential still being actively explored.